Afternoon, good evening, depending on where you are in the world. Eamon Darcy's my name. I'm the founder and operator of QUECWA, the Quantum Education Centre of WA. And today, I've got Donna. Look, Donna, I've got your caption up, not mine. Today is a bit of a run through and a bit of a talk about anything. Just give me a second while I get this right. There's so many things. Where have my captions gone? Oh, I know. Here we go. This is me. And I'll take off the ticker tape. So many things to do when you're live streaming. But look, it's so exciting. There's so much going on in the quantum world at the moment. And what we want to do is get a project called Q Girls up and running. Donna Buckley, who you'll meet in a few minutes, is heading it up, and she's getting things going at 1,000 miles an hour. And we're all, really excited. And next week we're going to have is our big day. So this time next week we're going to have a presentation. We've got Sadia from Dubai, a 16 or 17-year-old student. I'm not sure of all the exact ages of everybody. So, she's 16. She's only 16. Wonderful. So, yeah, we've got one presenter, 16-year-old high school student, and we've got 4 presenters, 4 panelists from WA as female high school students. So it's really important, and we're really getting the message out there. So the world of quantum computing will change everything. Jeff Bezos always says that quantum computing is the technology of the future. These are his words. I'm literally not exaggerating when I say it will change everything, and it will, because of the way it works. And we're going to start talking about how it works. So just keep asking questions. You can ask questions from the chat. So please say hello on the chat. I'm here looking after the chat as well. So if you're watching this on YouTube or Facebook, please ask a question. And, we'll really get into it and talk about it. Now, the actual topic next week for the big presentation will be on quantum pseudo-telepathy and the science. Now, when you hear the word telepathy, you start thinking, do-do-do-do-do-do-do. And telepathy, now I don't want to upset anybody, because I know a lot of people think they're telepathic, but telepathy, just for the record, has never been proven scientifically. So but quantum pseudo-telepathy works all the time and is currently used by the US government and many other governments in the world. So notice it's pseudo-telepathy. It actually has the effect of being telepathic when you're actually not. We're so lucky to have Anna Naden, who I'll introduce in a few seconds here. She's actually putting this effect, quantum pseudo-telepathy, into a quantum application, a quantum program. And I think, Anna, correct me if you're wrong, but the only person in the world doing it. It is so exciting. And one quick point before I start introducing the panelists is that the US government has just decreed, President Biden has just authorized the migration of every government document, imagine how many billions that is, on every current RSA encrypted server or encrypted server to be migrated as soon as possible to a quantum resilient net server. So that's what we call PQN, post-quantum cryptography. So the US is spending millions and millions of dollars on doing this, and they're doing it right now. Now, why is it urgent? The reason that it's urgent is because quantum hackers will be able to crack all of the codes used around Earth at the moment. If you're technical, I'm talking RSA encryption. So, wow, it's unbelievable that that's how important it is. And I can tell you now, at the moment, a lot of our cybersecurity isn't embracing post-quantum cryptography. So that, again, is a wonderful opportunity for everybody. So what I'm going to do now is bring on everybody, and we'll have a quick chat. So here's Donna. Wow. So let's see. Anna, you're on blank. Boom, boom, boom. Have I got everybody on there? Yes, I have. Wow. Okay, everybody. I'll start with you, Donna. Can you introduce yourself and
Amon, tell us? I don't think I'm visible, Amon.
No, but your camera's not on.
Yes, it is.
I've got here that it's not. It's what it says here. Your video's not streaming. Have you got your video on?
Shall I start? Well,
yeah, you start. Anna,
yeah, video. So my name's Donna Buckley. I'm a mathematics teacher turned cybersecurity. My interest in quantum, I suppose, I always come from a cryptography, has fascinated me. The idea of locking and encryption and using codes, and the fact that at the bottom of that is number theory that could be, 300 years old, that people were using simply for fun. They would do, and then they found a use for it with public key encryption. And the fact that the quantum computer will be that I know my understanding is very limited, but the fact that it will be able to factorize really large prime numbers so fast and break this encryption, and then we're going to need to find new encryption, has fascinated me. So I'm excited to bring my skills I bring from the Maths Association of Western Australia with student activities and girls, and let's get quantum out there to girls. And I'm really excited to partner with QUECWA in this project and inspire the next generation.
Oh, fantastic. Thank you, Donna. Are you, you teach cybersecurity.
I teach year 11 and 12 cybersecurity and mathematics. I've been in mathematics for 20 plus years. Cybersecurity, started teaching with 12-year-olds, year 7s. We were doing the RSA algorithm. I unpacked it with some year 7s. So that was fun. It was, yeah. And sometimes I think it can be accessible, and that's what I'm quite love about this project as well. We're making it accessible to young people, and now, my first lot of year 12s graduated this year from their cybersecurity course. So
wow, fantastic. Are you hearing anything in the market about PQC post-quantum cryptography?
No, it tends to be in the encryption, no one's really talking that. Encryption basics, hashing, at the moment it's more about awareness of your password security, and people just are not aware of their risk and the threats and that human error. It's still, I think it's an area that's going to progress, and people are going to have to start listening to, like you just said about Joe Biden moving the files.
So, yes. Yeah, people are going to. I
suppose it takes a while to trickle down.
Yes. But it's so great for our young students, because if they start learning this stuff, they're going to, be free up to do whatever they want. There's some links coming in on the chat, but I'll ignore them for the moment. So look, thank you for that. I'm just going to go around the clock. So Raja, can you tell us a bit about yourself, please?
So I do some cyber school. I don't really know much, but I think it's really interesting.
Yeah, I mean that you're exactly the sort of people we want to be talking to, because it's all new to you at the moment. Let me assure you of one thing: it won't be long before you understand more than you realize. Because. Oh yeah, and by the way, Raja, if you can just get a little bit closer to your microphone. Donna, we could hear everything you said quite easily, but yeah, Raja was a little bit faint. But it really is a fantastic opportunity for yourselves and anyone of your age. Now is the time to learn things like quantum cryptography, as well as the basics, because wait until you hear Sadia's speech. It's it really is out of this world. So okay, going around the screen, Hope, can you introduce yourself, please?
All right, so I'm Hope Cooper. I'm a Year 9 student at John Curtin. And yeah, much like Raja, I don't know much about quantum at all, but I know how vital it's going to be for like the future and the progress of technology. And so that's really interesting to me.
That is excellent. Again, that is what we're looking for: curiosity and an inquiring mind. And I loved one thing you said there, that you understand the importance of it, because it really is going to change the world. Donna, would you like to just say what you've just sort of said? What you typed in the chat?
Yeah, I was just going to search and get a name.
Oh, right. Yeah, because Eddie Wu won the Australian of the Year, and it was Michelle Simmons won Australia of the Year for the work she's doing.
Yes, Michelle Simmons, thank you. Yes, I remember.
Wonderful.
That was when it might have been 2018, where This Is the Future,
yes.
And it was the future of mathematics as a mathematics and a quantum technologist.
Is Eddie Wu involved with quantum?
Oh no, he's a maths educator, but he was the he was the People's Award, and then the Michelle won the actually Australian of the Year.
Correct. I'm a great fan of his. Who isn't? He's just brilliant. But yeah,
I'm sure Eddie Wu would be a supporter of us doing quantum.
Oh, he would be. He would be, surely. I actually, in my master's,
I've met him many times, and he loves. Yeah, he loves curiosity and all things.
Yes. He's a wonderful man. He is. He is wonderful. Yes. The only word for him. Okay, so going around the clock, Sadia, can you tell us a bit about yourself?
I'm Sadia Sarkib, and as Eamon previously said before, I'm 16. I'm doing my A-levels, and I took maths, physics, computer science, and economics. And I first got into quantum physics when I heard about how it was possible to have completely random numbers and completely random values. And I was extremely taken aback by that, so I decided to look into it, and I found something that I really loved. So.
Oh wow, fantastic! And of course, you and I have chatted a good few times now, and your knowledge on things like quantum entanglement and superposition. I might get you to say a few words about them if you wouldn't mind.
About superposition.
Yes.
So would you like me to kind of explain what it is?
Yes, I would.
Quantum superposition is essentially when a particle or quanta is in two states at the same time. So I like to think of it as a coin. So it's either heads or tails, right? But when it's in superposition, you can imagine that it's like spinning. So you can't, unless you measure it, you can't tell what its final value is, whether it's heads or tails or anything in between.
Wow, wonderful. I just love your knowledge. And in fact, that's not even what she's presenting on. She's presenting on quantum entanglement. In fact, give us a quick quantum entanglement.
So quantum entanglement is like when you have two particles that can be at any distance, but when one changes state, the other will change opposingly. So it's kind of like if you have a right shoe that's been made here on Earth, you will always have a left shoe no matter what. I guess that's kind of how.
Yeah, that's funny enough. That's what quantum entanglement is this mysterious connection, a connection between two very, what we call non-local objects. So they could literally be in different galaxies, and yet they perform as if they were one. It's just amazing. And obviously there's a lot more to it than that. But again, just imagine, you've got one particle here, well, two particles on Earth, you entangle them, you put one on the moon, one on Earth, you push the one on Earth a little to the left, and the one on the moon goes a little to the right. And no one knows how. Einstein spent his life working out how, and in point of fact, 3 physicists just 3 months ago got the Nobel Prize for Physics for proving that quantum entanglement exists. It's real, because there have been lots of loopholes and things. And there's a thing called Bell's inequality. I'm going far too far ahead. But the wonderful Anna, whom I'm about to introduce now, has done so many presentations on Bell's inequality, which was the first time Einstein was proven wrong. But look, I'll pass it over to you, Anna. Anna is wonderful. It's the only word to describe her. I went to one of her presentations, and I go to these presentations 3 a day. I'm constantly looking at global presentations around the world, as you girls should as well from now on. And I went to one of Anna's. I didn't have a clue who she was, and within 3 minutes, I thought, this is someone who knows the stuff and takes no nonsense. So with that introduction, I'm going to pass over to you, Anna.
Thank you, Eamon. Yeah, we've been working together for, 9 months now, I guess. And so in my youth, I wanted to be a professor of physics. And so I was in a PhD program. I developed a medical problem that basically made it impossible for me to do physics. And I dropped out with a master's. Decades later, I won't say how many decades later, but many decades later, I recovered, and I picked up a physics book about 5 years ago, and I've been pursuing physics pretty methodically ever since. Several years ago, I organized a quantum computing meetup. Meetup is a social media platform for people who gather around common interests. And it was in person mostly. I stopped doing that, but about 1.5 years ago, I started an online meetup group on quantum computing. Entanglement has been a theme in many of my presentations, but I got interested. Eamon put me onto this Magic Squares game that's the focus of this event. And I decided to really dig into the mathematics of it. And I did. And first I simulated the quantum system to try to prove that there really was pseudo-telepathy. And then eventually I actually wrote quantum software and uploaded it to quantum computers and ran it. And it was a rough go. A lot of times we'd get the right answer only 20 or 30% of the time. But I eventually found a quantum computer by a company called Quantinuum, a spin-off of Honeywell, that was adequate to the task. And I've actually gotten 97.5% accuracy out of that. So that was really nice. I got 80% with IBM's machines, and I got a $300 bill from them. Now they waived those charges for some reason. I don't know why, but when I visited my account, the balance was zero, so I didn't have to pay it. But Quantinuum has the best machines, and it really is a valid phenomenon. I've demonstrated it. The only difference between pseudo-telepathy and my program is that I have one quantum computer handling the activities of both players in the game. In the real world, you'd have two entangled quantum computers. So I think that's probably enough for me for this moment. Thank you.
Oh, thanks, Anna. And I can't believe you're getting up to 97% on your programming. Just so that everybody knows, we're talking about a game which you can't win. In fact, I might even just it'll only take me 5 minutes I'll put you guys backstage and I'll just show you this game. Oh, God, come down. I can't get rid of the download. Oh, okay. I'll just leave you guys up at the moment, but if you can all just watch this for a second. I am constantly being asked, oh, how fast are quantum computers? And I say, look, for certain operations, they are literally thousands of millions of times faster. But I say, now this is the game, but I say that really the important thing is that quantum computers can do weird, illogical calculations. And, these are weird computations that are currently being used by the, I'll just put the others back up, currently being used by the US government to get in fact, back to what Sadia was saying about true random numbers. Now, I'll just go through the game quickly because it's so simple. And you will see straight away that it can't be done yet on a quantum computer because of entanglement. So, Raja and Hope, if you can remember, entanglement is where there's this freaky weird entanglement between two particles that could be a million miles away, yet they are in contact with each other in a way that we don't understand. And by using them, and this is what Anna has simulated, we can actually win games like the Paris Merman, and I'll show you now. So what happens is, in the Paris Merman, you have a 3x3 grid, just like tic-tac-toe or noughts and crosses. Now, we may have, for example, Raja and Hope playing together. So Raja may be blue and Hope may be red. And what you have to do is the blue team, Raja, she can only fill out the rows and she can put ones and zeros in the row. But there's one more rule. She must have an even number of ones. So do we all understand that? So if we were playing a game
Sort
now, yeah, it makes sense in a minute. I'm condensing something that normally takes an hour to learn. I'm condensing it into a few minutes. But look, Raja, she has to fill one of the rows, and she has to have an even number of ones. Hope, on the other hand, on the same 3x3 matrix, she has to fill out the column, and she has to have an odd number of ones. So, that's almost the only rules. But let's see what happens when we, introduce a referee. So, do we understand that? Raja would do the rows, and they have to be even, and Hope would do the columns, and they have to be odd.
Could you show us a filled board with the ones and zeros?
I'm about to. Yep. So, for example, here, so they have one row, one column. Therefore, there's always going to be an intersecting square. And the way you win the game is if that intersecting square is of the same denomination, i.e., it's either a 1 or a 0.
Now, in a real game, you'd only have one row and one column filled in. You wouldn't have all 9 squares.
No,
right?
That's right. I think I've got that on the next slide, which makes more sense. Oh, that's just we're all playing it around the world. No, I don't. Yeah, so Anna's point is valid. This is a completed board, but if you can imagine the 3x3 with one row, one column, and the intersecting square has to be the same. Now, what happens is there's one more rule, there's a referee. And so Raja and Hope can collaborate before they play the game. As soon as the referee starts the game, they can't talk again. They're like they are in different galaxies. But they can set up a system whereby the overlapping square is either 2 zeros or 2 ones. That's what they want to do to get it the same. But what happens is the referee dictates which row it goes into and which column it goes into. So Raja doesn't have control over which row she puts it in, the top, the middle, or the bottom. She just gives the 3 numbers to the referee, and then the referee will randomly place it. Now, when you think about it, and I'm going to be quick here, but and I just want to say, I played it earlier this year with people from all over the world, and after 4 games, we basically lost 1 out of the 4 games. Nobody had 4 out of 4. And here's the reason why. If you can imagine this square here, there's all, so the 3x3 matrix, and you can see that the matrix follows all the rules, and there's always one square. If you look at the question mark down the bottom, if I put in a 0, it means the rows are odd, not even. Can we see that? And if I put in a 1, it means the columns are even and they have to be odd. So you can only win this game once in 8 times out of 9. there's always going to be a time when the intersecting square is basically the question mark. It can't be 0 and 1 at the same time. Or can it, like Sadia mentioned before? And the answer is in the quantum world it can. But can you see how classically you can't win this game?
Specifically, if you put a 1 in, then the third column is wrong.
Yes. So where that question mark is, it can't be 1 and 0. If it's a 0, do you see how the row is now got an odd number? Of the bottom row will be 0, 1, 0. And that's an odd number, so you can't have that. And if I put in a 1, then the third column will have an even number of 1s. I mean, don't worry about the intricacies of the game, although, we can talk about it. I'll answer any question on it. But the important thing is that you can't win it every time. You just can't. In point of fact, when after playing it 24 times, the chances of you winning all 24 games is 1 in 1,000. Now, when I played it with teams from Malaysia, India, the US, the UK, and Australia, we all had a lot of fun, and we all realized you cannot win this game. So that's all you have to remember, is that you cannot win it all the time classically. Yet, and this is what on the night when I said this, they simply could not believe it. I said that when played with entangled qubits, and a qubit is a quantum particle that is in superposition that Sadia explained earlier. In fact, all quantum computers are merely, ignore all the great big hardware, the dilution refrigerators, it's basically just a subatomic particle that's still in superposition. And when we play the game with the, particles, entangled particles, we win every time. And no one can explain that classically. I'll just take that back out. So this is just a weird proof. It's very complex. What the programming behind it is very complex, and the way the magic square is set up is very complex. But a quantum computer, 2 entangled qubits, will win this game every time from now to infinity. Why? Because it's weird. It's connected by this quantum entanglement. And there's also a thing called quantum contextuality, which means that a quantum particle, the reality of our universe, doesn't exist in a way that we know reality. The quantum contextuality says that the particle will be depending on how the context in which you view it, which in a subatomic particle might be the angular momentum, or it could be the energy of the particle. But the way you measure it changes. Well, it doesn't change it because it's not changing. It's just the way the quantum particle depends on the context. And this is what Anna's proving. Now, I know I've done that really quickly. Any questions on that? Even from the audience, I'm happy to take questions. Anna's the main one.
No, we've been having a little chat as panelists in the background and just thinking that's just, like you said, literally a game changer, and what Anna's doing. I'm really excited for next week to hear more. that 97.5% certainty through the quantum. It's fascinating.
I do stress it would be 100% if it wasn't for the computer. It's the hardware's the problem.
Yeah.
Because of a thing called decoherence. Yeah, Sadia, do you want to talk about noise decoherence?
Sorry. So noise or decoherence is kind of like when there's external forces acting on like the actual qubit, because you can't exactly cool anything to 0 Kelvin just yet. So there are still forces acting on the qubit, which causes noise. And that's why it would be 97.5 and not 100.
Yeah. Anna, do you want to add anything to that?
Well, I want to mention that temperature is a big part of it. The real challenge, I mean, what Sadia has said is exactly right. The challenge, it's an engineering challenge because you want the qubits to be isolated and not sensitive to their environment. But in order to do a computation, you want the qubits to respond to one another. You want them to be coupled. You want them to interact. And so it's a contradictory requirement. You want them to be isolated, and yet you want them to be responsive. And it's an unsolved problem, but this company, Quantinuum, which is a spin-off of Honeywell, has done a pretty good job. What they do is they move the ions. Ions are atoms that have had the electrons removed. They move them close together, let them interact, and then move them far apart. And that's their way of dealing with this engineering challenge.
Yeah, thanks, Anna. I should add there are many different forms of quantum computing at the moment. What Anna's referring to there is trapped ion, whereas you have superconductivity, and in our own UWA we have nitrogen vacancy, which is a diamond-centered computers. You've got photonics, which is a main one that's actually using light, because any subatomic particle has these weird forces of superposition and everything. So Continuum, which is Honeywell and IonQ, which was a quantum startup. We know the vice president of that very well, and she's also the president of Women in Quantum. So we'll be talking to her soon. But look, I'm interested in hearing from Hope and Raja. What do you think about what Sadia said about quantum entanglement? What do you think about? I mean, the best place to start is superposition or quantum entanglement. What do you guys think of that? Please feel free to.
I mean, I find it interesting how like two particles that are far away from each other become entangled, and I'd like to like learn about how they become entangled, and like why it's those two and not one with another one. And so I think that's really interesting.
Oh, that's Anna, do you want to answer that? I'd love to answer that, but do you want to answer that one?
Well, the real answer is nobody knows, because there's no force, there's no entanglement force that causes one particle to influence the other. And it happens instantaneously. It's not limited by the speed of light. So this looks like a contradiction to Einstein's theory of relativity, and it upset Einstein greatly.
Yes.
I think it's fair to say that nobody understands entanglement. It's got to do with the nature of reality and the meaning of the word fact, so that you have facts about the two particles, and somehow there's a correlation between the facts that are in reality for the two particles. That's the best I can explain it. You can look at my YouTube videos where I go into more detail, but basically, I don't think anybody understands entanglement yet. Although it has been experimentally demonstrated, that's what the Nobel Prize was for this year.
Yeah, I'm just going to put you. No one understands entanglement, but to entangle two particles in a laboratory, it's very, very easy, and it's done all the time. So you can get two photons, for example, which has polarization rather than electrons that have a spin, but you merely put them under a laser, basically a BBO crystal. I don't know what BBO stands, barium, bohrium or something, and whatever. But it's very easy to do, and then you can move those particles very far apart. Now, so do you understand how it's something that's done every day? So it's not hard to entangle two particles, but from then on in, we don't understand how on earth it happens. And so, did you want to say something?
Sorry. I was just saying, like, entanglement relates a lot to things like quantum gravity. And it was recently discovered, I think it was a group of researchers from MIT, Caltech, and Harvard that kind of created this abstract, like, 2D wormhole. It didn't actually, like, rip physical space-time or anything, otherwise, like, we'd all be dead. But it kind of, they had two entangled qubits, and one transferred information to the other through that sort of wormhole. So yeah, just a new thing. It's like, I think it was only 3 days ago that they announced it.
Also, the electrons in an ordinary atom of helium, which has a pair of electrons, they're entangled too. Or oxygen, or any element. All the electrons in an atom are deeply entangled. The difference is, of course, they're not separated from one another.
Yeah, good point. There's also, and this is not accepted science, but it's interesting, that at the time of the Big Bang, everything was entangled with everything else because it was, one quasi-subatomic particle, let's say. So we have found entanglement, and correct me if I'm wrong, but we have found particles that are entangled naturally. So entanglement does occur, like you just said in Ebert's atoms, but entanglement does occur in nature. And there's conjecture that when, at the time of the Big Bang, which is the start of our universe anyway, everything would have been entangled, which is why particles can be a huge distance from each other, but entangled. But I hasten to add that that's not accepted science. Because quantum physics is so weird, there are interpretations. So we don't know what's happening. We know it happens. In point of fact, quantum physics is way more accurate than Newtonian physics, or like anything we can simulate or optimize or calculate using, gravity and any of the fundamental forces is normally accurate to around 4 or 5 decimal points. Quantum effects we can predict to 13 decimal places. So it's extremely accurate that we know it exists, but we still don't know what's happening. And you've got things like, which we won't go into now, but if you want to do a bit of research, you've got things like the Copenhagen interpretation, which is the most used or the most followed interpretation, which is this collapse at superposition. It means the subatomic particles in this strange superposition, but if you observe it or measure it, it collapses to a distinct particle. And that is borne out in what's called the double slit experiment. Donna, do you teach the double slit at schools in WA?
I think I'm getting a bit of lag here. I don't know. It's not quite coming through.
Oh, sorry about that.
And obviously, I'm teaching mathematics, not science, as well. So there is differences there.
Right. Okay. But look, the double slit is a well-known experiment. It's on my channel, and it's also on Anna's channel, and it proves superposition. So, yeah, and a quantum computer can only do its calculations when it's actually in a state of superposition. So when that collapse, so there are interpretations with what's really happening, because we can't examine it, because whenever we look at it or try to measure it, it collapses and it's not in superposition anymore. So there's been, Bell proved that the particle exists before we look at it. It does start getting weird now. But look, we've covered an awful lot. And girls, do you have any questions? The Raja and Hope? Schrodinger's cat, of course. Yeah. Sorry, go on.
Already. But how was it discovered?
Great question.
What was the question?
The question was, how do you mean, like entanglement or superposition? Which one, or both?
Entanglement.
Yeah, so how was entanglement discovered? Anna or Sadia, would you like to answer that?
Go ahead, Sadia.
Could you repeat the question? It was a bit laggy.
Yeah, the question is, how was quantum entanglement discovered?
It's kind of like as I'm not exactly sure how it was discovered, but I do know that loads of physicists were researching it. I think Einstein said it was spooky instantaneous action at a distance. But yeah, I do not know how it was discovered. Sorry.
Yeah, well, it's just that when scientists first developed the technology to look inside of an atom, and we're talking 1920, so we're talking 100 years ago, they actually found that very many strange things were happening, like entanglement. So they expected to see, I don't know what you're taught at school in the science classes, but they expected to see, when they looked inside an atom, a nucleus with electrons flying around the proton and the neutron. But it's not like that at all. And they said, oh my God, it's strange. And then they realized there was superposition. And then they did all these experiments like the double slit to find out that superposition is real. And the same thing, the same thing happened with entanglement. They realized that they could entangle two particles and that the actions were correlated in a way that we don't understand. And we still don't. And in the 1980s, a very famous physicist, Richard Feynman, said, look, we don't understand this stuff. Possibly we never ever will. But we can build computers. We can reference to the superposition. And we can perform state transformations using linear algebra. So it's really great. Hey, look, guys, we've actually been, I don't know how long we've been 50 minutes. Please, if you have to leave, you certainly can do so. I know it's the session has been recorded if you want to look at it again, and I'll put it up on the website. But we probably should start closing. Is there anyone, yeah, with the question, feel free to, Donna, if you have, I know you've got an engagement. If you have to leave, yeah, just I'll put you backstage.
Yeah, I'm really looking forward to our next session, hearing more. Our women, and I've had a touch of it today, and I'm really excited to learn more. So, but yeah, and come back next week.
Wonderful, thanks for Donna.
And questions ready.
Yes, thank you for that. That was the point of the session, that we're comfortable with the way it works. I'm not sure what we can do about the time lag. Obviously, you've experienced some, but we'll see how that goes. But I'll let you go, Donna, and talk to you soon. So, girls, do you have any general questions for Sadia or Anna? No. And what do you think about superposition, for example? Raja, what's your thoughts of what's actually happening with superposition and entanglement?
Really interesting. I understood entanglement better. I think I'm used on superposition, so I'll have to look here.
Yeah, you're actually fading in and out with your audio for some reason, but yes, superposition is a very, very complex subject. And what is really going on is even more complex. But there's, I may just add, there's an experiment called the Delayed Choice Quantum Eraser, which is built on superposition, built on the double slit, and it indicates that events that have already occurred can be altered. So just think what that means. And this is at the quantum level. It's like you could write a code on an atom that doesn't exist yet. Very, very weird. So please don't think you should understand it after one very basic session like this. Do look at my channel. Do look at Anna's channel. And do look in general. You're in a wonderful position in this day and age that you can very quickly get information. If you type in what is superposition, you'll get 10,000 articles. And Hope, how about you?
Yeah, same with Raja. I think I understood the entanglement more than the superposition, but
Yes.
I'll look into the superposition and like try to understand it a bit more, hopefully, before like next session, you know?
Oh, well, that would be wonderful. And please feel free to email me if you've got any questions. Don't waste time studying the one thing a lot, because we can possibly just answer it for you straight away. Well, this has been a very useful session. It must be getting late there, Anna.
No, it's not late. I mean, it all depends on what your point of view is. For me, it's early in the evening.
Yes.
My channel on YouTube is Quantum Computing with Anna.
I've got it here. I was looking at it before. Keep talking.
Well, that's all I wanted to say, is just to point people to the channel. There's a lot of videos. Look at the ones that were produced more recently, because I did a better job on those.
Yeah, isn't that the way? Look, I do have your channel somewhere, and I will have that next time that I can keep advertising your channel. And to wrap up, Sadia, from you, how have you found today, and any comments?
It was really nice. I was a bit nervous with the presentation, but I guess it was fine. It was great meeting everyone. I'm just like a bit, because there's no like comments in the chat from the audience, so I just wanted to ask if anyone had any questions there that any of us can answer.
Well, that's yeah, that is a very good point. I think what you'll find is that next week there'll be lots of questions. What matters is that we all send the link to our friends and get them to include, to send it to their channels. And you'll find we normally, I'm only sending it to a smaller population than I will next week. So we will get questions coming in. So that's great, but it's great. And I love the way that you spoke about the wormhole. Anna, have you read that about the, you're skeptical, aren't you?
I'm not skeptical about that experiment, but I haven't gotten to it. This week I've been focused on technology because I have to make some money. And so rather than pure physics, I've been reading about or studying cloud computing. So I don't know about the wormhole, but I believe it because it's basically got to do with time, and it's probably related to that quantum erasure experiment where the effect can precede the cause.
Yes.
Only in quantum mechanics, only because of the uncertainty principle. I think it's fascinating, and I'm very glad you brought it up, Sadia. I will probably look at it. I'll take a break from my technology.
Fantastic. Yeah, well done, Sadia. I'm so glad you brought that up because that is interesting. And we all need to look into that a bit deeper. Okay, look, I think we should wrap it up now. It's been an hour. Raja and Hope, it's been lovely to meet you. Thank you for your attendance. And we'll talk soon. So I'll send some emails to you all, and we'll get ready for the big day next week. And it's going to be fantastic. Thank you, everyone.
Thank you. Bye.
Bye. Nice meeting you all.